In this video, we'll move into section 11.6, and we have two concept ideas that we need to get into. The first will be a discussion about the difference between absolute and conditional convergence, and then we'll move into our last two tests. We will discuss the ratio and the root test. So, first thing, up to this point, we've only been asking, do the following series converge or diverge? But now in this section, the book makes a distinction between the idea of conditional convergence and the idea of absolute convergence. I'll explain what the deeper meaning between these are in just a moment, but for a straight definition, a series is absolutely convergent. So the series A sub n is absolutely convergent if the series, the absolute value of A sub n, converges. That sounds very simple. And for some people, this becomes what they call the absolute convergence test. So two quick things. First, our book in this section does try and make a little bit of a point. Does it converge absolutely or converge conditionally? I'm not really worried about that. That's not going to come up on a test. But this still provides us an alternative way to determine convergence, if, once again, the logic works just like this. So, a good example. Let's look at the series minus 1 to the n over n squared. If I look at this series, all of this is my A sub n, and now, little things we can talk about. Hey, this piece would make it alternating. So if you kick that out in front, 1 over n squared would be B sub n. So again, realize A sub n is just used as my generic notation here. I'm not trying to do anything more than that. So all of this is my generic A sub n. So if I take the absolute value of that general term, what happens? Well, the big thing happens right here. Minus 1 to the n power, that's that alternating piece that keeps flashing -1, +1, -1, +1. You take the absolute value, I should say, and now all of those just become +1. So that -1 to the n power would just become +1 to the n power, and 1 to the n power is always just 1. So this would become 1 over n squared. Looking at this as a series, we would already know, well, that's a p-series, and specifically a convergent p-series. Therefore, we can come back to the original and say this series converges absolutely. So that's how some people can make use of this new idea. But it for our purposes, it's only useful if we see exactly what I just showed you. I saw a series that does have some negative terms, so by taking the absolute value, it makes a subtle change to the series itself, and then that new series, again, I'm looking at the underlying sequence, but the new series that goes with that sequence would then be a convergent series. So therefore, back to the original, this one also converges, and we can conclude that it converges absolutely. But to show you a secondary example where that does not work, just switch the n squared to a plain old n. Now again, these don't always have to be alternating series. These are just two examples to distinguish between these two different types of convergence. Because if I try the same technique here, and that's what some people misunderstand, the logic has to be perfect. Because if I take the absolute value here, that's all I would be left with. And that's the harmonic series. You could call it a p-series, again, p equals 1. But it's also the harmonic series, and we know the harmonic series diverges. So just taking the absolute value, that didn't do anything for me in this particular problem. Here it worked, but it only worked because after I took the absolute value, I ended up with a convergent series, and that allowed me to go back and say the initial converged. But here I'm ending up with a divergent series, so that tells me nothing. Does this converge? Does it diverge? I have no idea. This just didn't help. But now if you continue to work on this, you can note that it is an alternating series. 1 over n would be the b sub n. This does go to 0 as you take the limit. This is decreasing. So you could conclude, and I'm not showing you the work. I said it, but I'm not showing you here. But by applying the alternating series test, you would find that this series does indeed converge. But since the original series converged, but the absolute value did not, that would specifically imply that this conditionally converges. That's the difference, everybody. Now, if there are no negative terms, if we just started off with a 1 over n squared, we already know that's a convergent p-series. The absolute value gives the exact same thing. That would also be absolutely convergent. So you go back and look at things like 11.3 and 11.4, all the problems there, all of those absolutely converge because every test, integral test, comparison test, they all relied on positive terms. So if you have all positive terms, the absolute value of the underlying sequence is the exact same thing, so this would always go hand in hand. The only possible times you might get a difference between these two series is if you do have negative terms, and then the absolute value makes a difference. So there's a couple of examples, but now the deeper meaning. What does it mean? What does that really imply if we know something absolutely converges versus if it only conditionally converges? And this has to do with order, okay? If a series absolutely converges, this is, for a mathematician, this is exactly what we would always hope for. Because if it absolutely converges, now the order of the terms really doesn't matter. You're adding the terms together, and whether you add the first term plus the second plus the third, or you started bouncing and adding out of order, you'd still end up with the exact same result. But in a conditionally convergent series, the order is why the test converges, is why the series converges. Thinking about this one, well, again, this doesn't converge. 1 plus a half plus a third plus a fourth, some of our instincts, this kind of feels like it might converge. That's why we took a little extra time looking at the harmonic series, because it has a lot of feeling that something converges, but feeling doesn't help us here. We need proof, and that's just given as a divergent series. But now if you throw in the negative, now if I expand this one, so if I expand this one right here, I get -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5. That alternation, that's why the alternating series test was so simple, because you had those alternating terms, but you need those alternating terms. This is where it's very interesting if you go look at some math history. This is where some wrong conclusions were made because people saw patterns, but they only saw patterns by moving terms where they wanted them to go. And this is another place where infinity makes that weird. If this doesn't go on forever, there's no issue. If I just literally wanted to add these first 5 terms together, well, it doesn't matter if I go this minus this minus this, then add these two. That's where we have some flexibility, understanding the operations themselves, and, just simple addition. A plus B plus C is the same as C plus B plus A is the same as A plus C plus B. As long as you're only adding a finite number of terms together, you could change that order no matter what and still get the same result. That's one of our properties of addition. But when these sums go off forever, now the order starts becoming more important. And you can't just arbitrarily change that order. But that's what absolute convergence allows us to do. So, like I said, it's something we have to discuss, but that's it. If you like that, you can make that work. But just to realize, that certainly worked, gave us that this converged, and it was fairly quick. But if you apply the alternating series test here, that's also relatively quick. 1 over n squared, the limit does go to 0, and it should only take you a moment to show 1 over n squared is decreasing. So it didn't save us a ton of time. And if this wasn't such a perfect p-series, if you made this minus 1 to the n over n squared plus 1, well, now you can't make such a quick conclusion here. So again, this first problem kind of gives some people a false impression that this is going to be a super fast test, but it's only super fast because I picked an example where this was such a quick conclusion after I took the absolute value. So again, absolute convergence, it's nice. It's a term we should have heard before, but thinking about our exam, I'm not going to separate into the different types of convergence. I still plan on having a big section, and it's simply going to be, do the following series converge or diverge? So now let's move into our last two tests, the ratio and the root test. Now, kind of a little funny, they're the last two tests we introduce, but in reality, they're probably our two most important tests. I don't want to make it seem like they're the only tests that are necessary. We certainly had to go through everything we did to get to this point. We had to do that for a reason. But now that we get to the end, these are in a lot of ways the two more common tests that get used. Not just on this initial section that ends in 11.7, but even as we go into sections 11.8, 11.9, 11.10, the ratio test in particular, that's still going to be very helpful and necessary. So what are these two tests? I'm going to write them up quickly down here, and then we'll get some practice. We'll see how they work, how they don't work, and just like all the other tests, try and keep an eye on what are the different types of series that these tests work well with. So, the ratio test, what we are going to do, we are going to start off with the series a sub n. So just like up here, don't worry about the convergence part, just a generic summation of a sub n, my infinite series. And what we are going to do, we are going to take the limit of the absolute value of the n plus first term over the nth term. And we will get some value L. That's all there is to it. This is very easily mistaken with the limit comparison test. But back then, we had two completely different series. We were looking at a series a sub n that was given to us and a series b sub n that we brought into the picture that was not there at the beginning of the problem, and then we compared them. The direct comparison had to check some inequalities based on b sub n, whether converge, diverge. If the inequality went the right way, we can get a good conclusion. For the limit comparison, whether we did a sub n over b sub n or b sub n over a sub n, it was all about just, do we get a limit value that is not zero, that is not infinity, and then the series a sub n converges, diverges the same way the series b sub n did. So very different here. Here, this is all the same series, but it's the n plus first term over the nth, and here we don't have a choice. Before I pointed out with limit comparison, I do a sub n over b sub n, you do b sub n over a sub n. Well, my limit is 3, your limit is 1/3, but that doesn't matter. They're both greater than 0, so we both get to make the same conclusion. But here it makes a huge difference. We all have to do the n plus first term over the nth term. Okay, I'm not even giving you the rest. That's what we're setting up. But before I give you the rest, let me point out the root test. The root test, we are also going to take a limit. All of these limits, this entire chapter, sequences, series, every limit is always as n goes to infinity. And this time, we will take the limit of the nth root of the absolute value a sub n. Some people prefer to write this in this form. Still include your limit notation, but just instead of the nth root, they prefer to write it to the 1 over n power. I shouldn't write equals here. That's just for your information to see that's the same thing, but without writing the limit, that would actually be a difference. And once again, we're going to get some value L. The reason I'm showing you both of these at the same time is because even though we're taking very different limits here, and don't overlap these, here they both have absolute value, but here a fraction, n plus first term over nth term, here a root, a radical, the 1 over n power or the nth radical, whichever way you prefer to write it. But don't mix these two together. Either way, we get some limit value L, and now here's how we make our conclusions. Either one of these, if the L that we get is less than 1, then the series A sub n, specifically we would get absolutely converges. This takes that absolute value into account, but for our purposes that would just lead to a conclusion converges. If L is greater than 1, then our series diverges. And there's no other diverges. Again, we're not going to do, there's no absolutely diverges, conditionally diverges. Divergent is still just divergent. So here's a nice thing just right off the bat, realizing that this is not a test that it's like we can only get converges or we can only get diverges. Either possibility presents itself, but notice there's still a big case that I haven't written yet. What happens if L equals 1? If that happens, that basically means we applied the wrong test. That gives us absolutely no conclusion. It's a little bit like, just to give a quick comparison, the test for divergence. If the test works, if the limit of the underlying sequence does not equal 0, you're done. That series diverges. But if the test doesn't work, meaning that that limit does equal 0, you get no conclusion. Anything could happen out of that, and that just means you need to try something else. That's the similarity that we get here. Now, before we do any problems, why would either one of these work well? What are the situations? Well, over here, anytime you have a factorial, we haven't seen factorials for a little bit, so we're going to see some more of them. They're going to come up here. And anytime you see a factorial, the nature of factorials, this ratio, good things will always happen. Things will reduce. But not only factorials, this also works really well when we have combinations. I'm just going to write combo for short. Combinations of P and geometric series. We saw if we have something that's almost a P series, comparison tests work well. Almost a geometric series, comparison tests again work well. But when you have combinations of those two, when you have n to a power and n as an exponent, this is going to be another good, helpful test for us. The root test, well, not quite, again, all these things, we don't have any set in stone rules, but we can still get, some common situations here. And if A sub n can be written as something to the nth power, well, then the 1 over n, or the nth root, and the nth power will simplify, and that often leads to a very simple result here. So just like all the other tests, getting some good practice. First, just applying the test, getting practice with the tests themselves, knowing how to work through either of these limits, practice with that. There's still limits, L'Hopital's rule, other possibilities, a lot of infinities floating around. So there's still a lot of just old limits that we need practice with and just some reminders. So just getting the tests themselves, some good practice, but also starting to get that feeling of why this test might work. Having that experience of knowing when these will simplify and make that a fairly simple limit, when this would simplify to get a fairly simple limit. That's kind of the second part to be really good with this section. So let's jump right in. Let's start off. So again, our pretty standard directions are still going to be converge, diverge. Converge, diverge, support your answer. just before I start doing some problems here, I want to point out another common little issue that students have in this section. It happens a little earlier in the other sections as well, but it especially comes up in 11.6. Students don't apply the tests. They see a few problems and they see a few examples and they start making up their own rules, so to speak, in their head. They see something that happened, they justify it in their head. Well, in this situation, that series converged, diverged, whatever. And then they try and just say in another problem, well, because of this, it converged, diverged. That's not proof. Again, apply the tests. That's what we want to get practice with. The tests are giving you the proof. The tests are giving you the support. So if you're just writing things like, well, if I do this limit, well, what test are you applying? That's a big part that we've always been stressing. There's a lot of notation, there's a lot of detail, so you have to keep track of that. And even if you just get the right answer, converge, diverge, if your test doesn't make sense, if you're not applying the test fully, only doing a part of it, but not showing everything that needs to be shown, that's not going to get you full credit. So just be sure, be clear, and ask questions if you're confused to make sure you're including enough information. But if you're following the videos, I think you're really getting a lot of good sense. It's not that you have to write a lot. You don't have to write sentences or paragraphs or anything like that. It's just enough to be clear. What is the test you're applying? And that you're covering all the pieces. For a comparison test, you're clearly showing the new series you're introducing, making a case whether that converges, diverges, and then running the comparison test appropriately. For the integral test, you're testing those three initial conditions, making sure they work, that they are confirmed, that all those three conditions hold, and then you get to run the test by testing that improper integral. Right? Alternating series. I mean, we can keep continuing. That's the idea. That's where we need our practice. So, problem number 1. Let's jump right in here. Let's look at the series 3 to the 2n power over 5 to the n minus 1 power times n cubed. That is a pretty ugly series. But hopefully with some good experience, we'd recognize components. If this stuff wasn't here, that n cubed, that n to a power, that's a p-series component. But then if the n cubed wasn't here, the other two pieces, the n is an exponent. The n is an exponent. Now they're not perfect exponents, but something to the n power, number to the n power. Both of these are geometric components. So this very first problem, these two are both geometric components. This is a p-series component. Now again, it doesn't have to be two geometric series components and one p-series. It could be multiple p-series and one geometric series. If the 5 wasn't here, this would still be enough to be a combination of a geometric and a p-series. All of that. Now you don't know why at this point, but just from what I told you on the previous page, this is that combination. So this is a place where the ratio test can help us. So let me be very full and clear in this first problem. And, with a little practice, we'll see there's little things some people do just to, slight shortcuts. Nothing major here, some slight shortcuts as far as not writing tons and tons out. But we're starting off the limit, n goes to infinity, absolute value. I start with the n plus first term. This is a sub n. So for the n plus first term, just like we did with our decreasing every time we had to check that, we replace n with n plus 1. Preserve all the other relationships. So this 3 to the 2 times n becomes 3 to the 2 times n plus 1. All in the exponent. 5n becomes n plus 1. The minus 1 is still a part of that exponent. N becomes n plus 1. The cube is still there as an exponent. All of this is a sub n plus 1 divided by the original, that is our a sub n. So, two things from here. you'll notice a lot of our series contain fractions. So starting off with a fraction, your n plus first term over your nth is now a very, very big, ugly fraction. So that's one thing that a lot of people start to shortcut. That when you're starting off with a fraction divided by a fraction, well, our first step of cleanup, dividing by this fraction, becomes times the reciprocal. So you'll see as I do some later problems, some people immediately, instead of taking this first step and writing this all out, they just immediately start writing the n plus first term times the flip of the nth term, getting ready for that cancellation. The second thing is the absolute value. Now in this particular problem, this absolute value is not doing anything. None of my terms are negative, right? N's are only going to be positive values. And look at what's happening here. Well, this is an n, that's an n, so cube it, that's always positive. 3 to any power, 5 to any power. Well, the 3 and the 5 are positive, so raise them to any power, they're positive. This is a nice coincidence that the absolute value is doing nothing. So before I take this limit, again, the whole point of the ratio test, don't just jump in and try and evaluate this limit. We're hoping things simplify in some way. And that is what's going to happen here. But first, I'm just going to clean this up a little bit. This will be 3 to the 2n plus 2. Here, the plus 1 minus 1 cancel. And that's as good as that's going to get. Dividing by this, I flip it, so I get a 5 to the n minus 1 here, times n cubed, divided by 3 to the 2n. And as I noted, the absolute values aren't doing anything here, so I can drop them. Some people, when we get to some negative terms, if I had negative 3 to this power or negative 5 to this power, well, then the absolute value would make that a positive 3 or a positive 5. Okay, so why does this test work well with geometric and p-series? Well, look at the geometric components. Think about rules of exponents. This can be broken down into 3 to the 2n times 3 squared. So the 3 to the 2n's can cancel. Similar here. There are a few other little ways people think about cleaning these things up, but that's the idea. Same thing here. 5 to the n minus 1 is 5 to the n times 5 to the negative 1. And by rewriting this in that way, that allows me to cancel these 5 to the n's. Now these don't cancel, but now that I've canceled these other pieces, these are the only n's that are left behind. This is all about dominant terms. Oops, this is 5 to the negative 1 here, everybody. Right? 5 to the n times 5 to the negative 1. So this is a 9. This would flip into the denominator as a 5. The n cubed is still on top. The 5 I move to the bottom. This n plus 1 cubed is still here in the bottom. And this is where now you can at least start plugging in, and you might end up using L'Hopital's rule here. But even without foiling all this out, n plus 1 cubed, the biggest term is going to be n cubed. So because I'm taking this limit as n goes to infinity, I get to focus just on those dominant terms. That allows me to simplify. This is the L value we were talking about back here. L is 9/5 or 1.8. That is a value that is greater than 1. Come back up here or just write my conclusion. So my series diverges, and we know that because we applied the ratio test. Now, first problem, some people do look at that and say, wow, that was supposed to be easy. Well, again, that's why I keep stressing, hopefully we've already had a lot of good practice with limits. They're not all quite as, I don't even want to say this is bad, because this is not that bad, but it does take some practice, especially these rules of exponents. Most people are a lot more familiar going the other way. that when you multiply these two with the same base, hey, that allows us to combine and combine by adding the exponents. But here we're just doing it in reverse. So there's some little other ways some people think about some of these cleanups, but that's something we need to get used to. And we're definitely going to see a lot of, dominant terms. Look for those things so that way we could finish and get good answers for these limits. Okay, let's move right along. Let's jump in. And now let's think about problem number 2. Same directions. In problem number 2, let's look at the series -4 to the n plus first power over the quantity 2n factorial. Okay, so now I take a look at this problem, and this problem, I see the factorial. Now, I will, right after we do this, I'm going to show you another quick follow-up with factorials, but factorials in general, as long as they're like this, and again, number 3, I'll show you what I mean, what a difference would be, but when you see a factorial, that is practically begging you to use the ratio test. No matter what the other pieces are. This happens to be a geometric component, but even if it was just an n squared and that was a p-series component, or it had both p-series and geometric component, again, the factorial, that is practically begging you to apply the ratio test. So I still don't want to rush you, so I'm still going to go slowly through this one, but I'll quickly follow up with my second line like I did here, and I have no problems if you feel comfortable jumping to that point. Okay? So the first thing, again, that gave me my big clue to try the ratio test. Well, the ratio test, again, we starting off setting up this limit. So as n goes to infinity, absolute value -4 to the n plus 1 over 2 times n plus 1 quantity, that whole quantity factorial, all of that is my a sub n divided by, my a sub n plus 1 divided by the original term. So very much like the first problem, everywhere there was an n, I replaced it with an n plus 1, preserved the relationships. I mean, some people literally, everywhere there's an n, they replace it with an n plus 1 and use parentheses. But sometimes, like here, quantity n plus 1 parentheses plus 1, that parentheses isn't doing anything. But here, that parenthesis is essential. If you just replace 2n with 2n plus 1 factorial, that's going to end up leading to a minor mistake. And you may luckily get the same conclusion, but that would be just it. It would be luck. So again, make sure not just that you're getting the test and you're running it correctly, but all the little steps along the way, plugging in and simplifying correctly are just as important. But now, several people, after a little bit of practice, not typically right off the bat, but after a little bit of practice, they kind of skip this step. The absolute value, well, that's going to get rid of the negative. That -4 becomes a +4, so both of these become 4 to a power. That's the only change. So some people just automatically, they don't even do this step. They already start cleaning up with the absolute value. They already start cleaning little things up like n plus 1 is n plus 2. Here, that if you distribute, that becomes the quantity 2n plus 2 factorial. And then here, instead of writing this dividing by a sub n, they already jump into multiplying by that reciprocal. So that's what I mean, everybody. Oops, I'm sorry, one little thing. This was an n plus 1 here, right? That was the original term, so there's still that same original term. So I did two big things here, and I can't say it enough for everybody. I'm not trying to rush you. I'm perfectly happy for the entirety of this unit, for the rest of the semester. If you need to write it all out every step of the way, that's just fine. Again, in class, if we're, taking a test and we have a 70-minute time limit, I might stress a little bit more, not writing too much out so that way you could get right into the problem and not waste time writing out too much. But having the comfort of working from home and having 24 hours for your exam, there's no harm at all taking an extra moment to write this and then moving to this line. But moving to this line, still not even close to done. I'm not taking the limit. You need it. Don't lose the notation, everybody. As I keep stressing, notation is important. If you just write this equals this without the limit, that is incorrect and will lead to small points off. So all this is necessary, but still, in a ratio test, I don't plan on taking the limit right off the bat. I always plan on something cleaning up. And these two pieces, just like we saw up above, here again, this is where some people, they don't even combine this because they see another way to cancel this. But plenty of people, they like to combine things when they can. And now this will become 4 to the n times 4 squared. This will become 4 to the n times 4. The 4 to the n's cancel. And even better, we get a little more that cancels. 1 4 cancels here with 1 4 down here. So know yourself, everybody. Some people need to cross these off to know. I already manipulated these to get these, so now they could be clear. This 4 is still here. Well, what else? Well, these two pieces, remember, go back, we did a little bit of this with sequences, and now we'll get some more practice. The bigger factorial can always expand to then cancel with the smaller factorial. This is the bigger one. So 2n plus 2 factorial will start as 2n plus 2, but then subtract 1, 2n plus 2 minus 1, which would be 2n plus 1. Keep going, subtract 1 again, and you get 2n. I stop there. I can keep going. 2n minus 1, 2n minus 2, 2n minus 3, but I stop there because these match. Don't forget your factorial. I'm not just crossing off the 2n's. It's the entire 2n factorial. This is what we are left with. And now just the nature of the problem. Up here, after I did all my cleaning up, I still had powers of n, so I did a little work with dominant terms so that I could finish with a limit and make my conclusion by comparing to 1. But then come down here, there aren't even any n's left in the numerator. If you want to FOIL this out, go ahead, but look what's happening. You're getting 4 over infinity, infinity. You're getting 4 over infinity. That equals 0. 0 is less than 1. So now our series converges by a ratio test. Okay. Still just getting our initial practice, getting some good practice, I hope. But now, like I said, if we started number 2, that factorial really guided us to this approach. But let me show you, again, just as important to see how these tests do not work as it is to see when they do work. So let's take a quick look at number 3. Let's look at n factorial over n plus 2 factorial. Let's take a look at that series. When I think of that series, well, again, those factorials may stand out, but the big difference is now there's 2 of them. And with 2 factorials, without even setting up the ratio test, I'm already can simplify this. And that's the better habit here. That if I can simplify inside my general formula, that's a good start. And this would simplify by expanding the bigger one. N plus 2 times n plus 1 times n, and it keeps going. N minus 1, n minus 2, n minus 3. But stopping here, put the factorial so that these cancel. this is what we'd have. And again, if you want to clean that up a little bit, that'll be n squared plus 3n plus 2. And this is not a ratio test situation. Again, I'll come back and show you if you just jumped right in because you saw the factorials. But after this cleanup, now we should see this is not a ratio test. This is a comparison test. Because even though this had some factorials, once I simplified it a little bit, what this really is almost a p-series. Get rid of that plus 3n plus 2, and you've got the p-series, p equal 2. That would be the better way to do this one. Compare to that p-series. Whether you want to do this one would work with the direct comparison. This would end up having the bigger denominator, so smaller fraction. And since you're comparing it to a series that converges, that is the way you want the inequality to go. Or you could do the limit comparison. That limit, if you compare this to 1 over n squared, would give you 1. This is not a ratio test. A ratio test getting 1 leads you to no conclusion. In a limit comparison, that would give you your conclusion that whatever the new series does, so does the old. So again, I'm noting that on the side. Compare to 1 over n squared, which converges. So that would be the better way to do this. If you just applied ratio tests to something like this, let me show you that. Both of these, either in this form or this form. So we saw in problem number 1, if you had a geometric component mixed with this p-series component, then ratio tests would work. But if all you have are p-series components, you try and run the ratio test here, you would end up with whichever form you prefer. I'll leave it in this form. I would have 1 over n plus 3 times n plus 2, because I'm adding 1, n plus 1 plus 2, n plus 1 plus 1. Dividing by the original, which I'm multiplying by the reciprocal already. You could cancel these two, that's true. That's a little lucky. But now n plus 1 over n plus 3, that limit equals 1. And again, that would be inconclusive, wrong test. Doesn't tell you applied the ratio test incorrectly. It's saying that you just use, again, not a bad thing to try, but to realize that gives me no conclusion at all. Try something else. That's where hopefully if we didn't see it right off the bat, now we'd see, oh, okay, ratio didn't work, but again, almost a p-series, so let's compare to that p-series. Run one of your comparison tests. But okay, you don't clean up the factorials right off the bat. You again just jump in with a ratio test. You'd have n plus 1 factorial over n plus 3 factorial. Again, divided by this, which I'm already going to flip. Absolute values, same thing here. Absolute values weren't doing anything. There were no negative terms. Same thing here. And now it's like, well, what to cancel? Well, we got all types of possibilities here. But I'm going to keep it a little simple, that if I expand this one, just one term expansion allows me to cancel these. And then same thing here, just expanding this one time would allow me to cancel these. And you're in the exact same situation you were here a moment ago. This over this, as n goes to infinity, you're once again getting 1. It didn't matter, right? Maybe that's not quite so obvious, but the reason both of these ratio tests worked out the exact same way with the exact same pieces left behind is because this was the exact same series. Whether you cleaned up right off the bat and then applied the test, or applied the test and then did some cleanup along the way, it's all the exact same thing. So again, number 3, let's be very clear, the ratio didn't work. So you would come up and apply one of your comparison tests. Not a bad thought to try it, but when we see it doesn't work, that doesn't mean we give up. That just means we try something else. We move on. Okay, So let's continue. We have several more that we want to take a look at here. Let's take a look at number 4. Actually, before we start number 4, let me start a new video. This is a good place to take a little break. We had a nice introduction. We still haven't seen the root test yet. So make sure you continue into part 2, because again, several more good problems to get some more good overall practice.